Hello students, welcome to ECLIMU Learning Simplified and welcome to this lesson. In the previous lessons when we were discussing measurements, we defined mass as the quantity of matter in an object. Now, in this lesson, we are going to see the relationship between mass and weight. My name is Albert. I hope you will enjoy the lesson. By the end of this lesson, I expect you to be able to define mass and weight, and of course give the relationship between mass and weight, which is going to be weight is equals to mass times gravitational field strength, and then give the SI unit of weight, and then define gravitational field strength, and also give the SI unit of gravitational field strength, and then finally you will be able to give the differences between mass and weight. So at the end, after studying definition of mass and weight, SI unit of weight and gravitational field strength, I will expect you to give me the differences between mass and weight. So be keen as you pick the differences as we learn from the beginning to the end. Now we are going to realize that mass and weight are related in a special way, but first we are going to define them separately. Mass is defined as the quantity of matter in a body. Quantity in this case means the size. And when we were discussing measurements, we said measurement is the process of finding the size of a physical quantity. Then remember, we said mass is a basic quantity. It's a basic quantity. It means it can only be obtained from a measuring instrument, and it cannot be obtained from dividing or multiplying other physical quantities. So this one you can get it directly. And then we said its SI unit is kilogram. That is what we discussed in measurements. Now, weight is the gravitational pull on a body. So if you have a body of mass, of a certain mass, and then it's experiencing a gravitational force. Remember we discussed the gravitational force. That one we are going to call it weight. Now, since weight is a force, because a pull is a force, since weight is a force, then it means its SI unit will be Newton, because we said all forces are measured in newtons, whose symbol is capital N. Then now, we said a force must have both magnitude and direction. Now, after finding the size of this weight, now how can you determine the direction of weight? The direction of weight is towards the center of the earth. If this is the earth here, this is earth, and then you have a body with some mass here. The force which makes it to fall towards the ground, that is gravitational pull or gravitational force. That's what we call the weight of that body. So we are going to see that whenever you have a body of some mass, it has its own weight, and the weight is determined by how much it's being pushed or pulled towards the center of the earth. Now, how is weight calculated? Before a student knows how to calculate weight, it's very important to know that weight is a derived quantity of mass. It means derived quantities, we define them as quantities that can only be obtained through multiplication or division of other physical quantities. So weight, we are going to obtain it by either multiplication or division of mass. But we are going to realize that for us to obtain weight, we are going to multiply mass. So we are going to use this sign multiplication. We are going to multiply mass and acceleration due to gravity, which we call gravitational field strength. So in this case, we are going to get weight is equals to mass of a body multiplied by gravitational field strength. Gravitational field strength is different from one place to another, especially when you move from one planet to another. But on planet Earth, on our planet, we have it as 9.8 newtons per kg. That is the gravitational field strength on Earth's surface. But when you move to the moon, you are going to realize it's 1.67, and when you move to Jupiter, you are going to realize it's like 20 newtons per kg. But it differs from one place to another. Now let's do a question so that we see how we can use the relationship that we have just generated between weight and mass. And the first question is convert 2 kg to weight. Remember, we are going to use our equation weight is equals to mass times gravitational field strength, and we are going to calculate this weight on Earth's surface where G is equals to 9.8 newtons per kg. So the first question now will go, the first one, we are required to convert 2 kilograms to weight. So first thing you do, you identify what you have. You have mass, which is 2 kilogram. Then you have gravitational field strength, which is 9.8 newtons per kilogram. And now you are looking for weight, which you don't know. So now what you do here, you write our relationship, that's weight is equals to mass times gravity. Do you have mass? Yes. Do you have gravitational field strength? Yes. So now you feed them directly, it will be 2 kilogram times 9.8 newtons per kg. Now per kg will go with kg into kg, then our answer will remain in newtons. Now our final answer of weight will be 19.6 newtons. Then the second question requires us to change number 2, 50 grams to weight on Earth's surface. So what we do, as usual, you identify what you have. I have mass, which is 50 grams, but is grams the SI unit? No, so you have to convert it to SI unit, which is kilogram. The relationship between kilogram and a gram is that 1 kilogram is equals to 1000 kg, or grams, I mean. 1 kilogram is equals to 1000 grams from the multiples and some multiples of kilogram that we looked at in measurements. Then now you have 50 grams. 50 grams, what will be the kilogram in 50 grams? Then you cross multiply, it will be 1 kg times 50 grams over 1000 grams. Gram will go with gram, then it means our answer will remain in kg. Then now our mass will be 0.05 kilograms. So now you have mass in SI unit. Then do you have gravitational field strength? Yes, which is 9.8 newtons per kilogram. Then now weight will be mass times gravitational field strength. Now in this case, it will be weight is equals to 0.05 kg times 9.8 newtons per kilogram. Now in this case, per kilogram will die with this kilogram, and then now our final answer will remain as weight is equals to 0.49 newtons. Now we have the third question here, which is requiring us to change 240 grams to weight. And now I'm not going to do this because this is your assignment now. So you are going to convert this into weight. And then if you get any difficulties, remember you visit ECLM website where you are going to get all solutions to these assignments that I'm posting. Now this has led us to discuss gravitational field strength that we have been using in calculation of weight. Remember, weight we have said is equals to mass times gravitational field strength, and this formula is very important because in physics, when you have this formula, it's like you have half of the physics on your fingertips. So we define gravitational field strength as a gravitational force or weight acting on a unit mass at a place. As a gravitational force acting on a unit mass at a place. At a place means different places have different gravitational field strength. If you are on Earth, the gravitational field strength is 9.8. If you move to the moon, you are going to find the gravitational field strength of the moon is 1.67 Newton per kg. And then when you move to other planets which are bigger like Jupiter, you are going to find the gravitational field strength is 20 newtons per kilogram. Now the SI unit of gravitational field strength is Newton per kilogram, which is written as an N per kg or Newton per kilogram. So gravitational field strength can be determined experimentally in our labs by going to the lab and set up an experiment where you are going to measure mass of different bodies in kgs, and then you convert this mass to weight in newtons. Remember, weight is equals to mass times gravity. For example, if we take our gravity G as 10, then now if we have a mass of 1, then gravity will be 1 times 10, which will be 10 newtons. If 2, 20 newtons, 3, 30 newtons, and then 4, 40 newtons. Now, if you draw a graph of weight in the y-axis and then mass in the x-axis, your graph will be a straight line from the origin, and then it will have a gradient or a slope. If you find a slope of this line, that is change in weight over change in mass, our gradient will give us the gravitational field strength. For example, if now you take, let's use the SI unit. If you take change in SI unit of weight is Newton, change in Newton over change in mass SI unit is kilogram. Remember, now we are going to get the slope. We are going to get newtons per kilogram. And remember, Newton per kilogram, we have said, is the SI unit of gravitational field strength. So if you have a graph of weight against mass, the gradient will give you the gravitation or gravitational field strength of the place where you measured your mass and your weight. So let's now do a few examples which will require us to calculate weight, mass, and even gravitational field strength of different places. Now the first question is, let me divide this working space so that we get enough space. An astronaut is a person who explores space, weighs 800 newtons on Earth. So we have on Earth, the astronaut has a weight of 800 newtons. And then where gravitational field strength G is equals to 10 newtons per kg. Now the first question, calculate his mass. We want to calculate the mass of the astronaut, is what we don't know. But do we know the relationship between mass and weight? Yes, mass or weight is equals to mass times gravitational field strength. Now, do we have weight? Yes, so it will be 800 newtons is equals to, do we have mass? No, time is equals to mass times, do we have gravitational field strength? Yes, 10 newtons per kilogram. So in this case, if we want to get the mass, then we will divide by 10 Newton per kilogram on both sides, 10 Newton per kilogram, like that. And then in this case now, 10 Newton per kilogram will go with that one. Then now we will remain with mass on one side. So it will be mass is going to be 800 Newton divided by 10 newtons per kg. This is very important. We should work with units all through. Then now after this, let's now solve this one. Our mass is going to be 800. Remember, when we say per, it means divide by. So it will be 800 newtons divided by 10 newtons per kg. 10 newtons per kg, like that. But now, when you have a division from your mathematics, if you want to make it a multiplication, then you introduce a multiplication and then interchange the denominator to become the numerator, and then the numerator become the denominator. Then in this case, if we do that, we will have our mass is equals to 800 newtons times, now the kg will become the numerator, which will be times kg, divided by our numerator now becomes the denominator, that is 10 newton. Now from this one, we have Newton here. It will cancel with the Newton on the upper part. And then this 0 will go with this 0. And then now our mass will remain as 80 kilograms. So the mass of this astronaut is 80 kilograms on Earth. And then the second question now, they want us to find the weight on the moon where the gravitational field strength is 1.6 newtons per kg. So in this case, mass of a body is the quantity of matter in a body. Mass does not change. So if we know mass we have, it's 80. The same astronaut who moved to the moon is 80 kg. That is the mass. Gravitational field strength of the moon we have been given as 1.6 Newton per kg. Now they want us to calculate the weight on the moon. So what we do, the relationship between mass and weight, it will be weight is equals to mass times gravitational field strength. Now in this case, we will have our weight is equals to mass, it's 80 kilograms, times gravitational field of the moon, that's 1.6 newtons per kilogram. Now kilogram will go with kilogram, then our answer will remain in newtons. So the weight now, weight will be 80 multiplied by 1.6, which is going to give us 128 newtons. So this is now the weight of the astronaut on the moon's surface. So as you can see, when the gravitational field strength is small, the weight will be small. When the gravitational field strength is as big as 10, the weight was 800, but it's of the same person, astronaut, with a mass of 80 kilograms. The second question is almost similar to what we have just done, but the places have changed now. The question reads, an astronaut, same astronaut, weighs 1,200 on Mars. So here we have planet Mars. The weight is 1,200 newtons. Then where gravitational field strength is 16 newtons per kilogram. Then the first question is calculate the mass of the astronaut, which is we don't know the mass. So what do we do? From the formula, weight is equals to mass times gravitational constant. Then if we need the mass, it means we will divide by g. Then now in this case, g and g will go, and then our mass will remain as weight over gravitational field strength. So do we have the weight? Yes, we have weight, as our mass now will be weight is 1,200 newtons. Then our gravitational field strength is 16 newtons per kilogram. Now in this case, a newton will die with newton, then mass now is going to be 75 kilograms. Converting this, for this one to move up, I have shown you back there, so it's not an issue now. Our mass will be 75 kilogram. Now mass does not change. Mass on mass, it will be the same as the mass when this same person goes to Jupiter, because it will be the same person. The only thing which is going to change is the gravitational field strength. Now the second question is asking us, this was the first question. Second question is asking us, find its weight. So we don't know the weight now. Weight is equals to what? Of the same astronaut on Jupiter, where gravitational field strength is 20 newtons per kilogram, and then the mass of this same astronaut is the same as 75 kilograms. So what you do, our relationship, weight is equals to mass times gravitational field strength. Do we have weight? No, that's what we are looking for. Do we have the mass of the astronaut? Yes, 75 kilograms. And then do we have gravitational field strength on planet Jupiter? Yes, we have 20 newtons per kilogram. And now in this case, kilogram, we'll go with kilogram, then we will remain with our weight is equals to 75 times 20 Newton, which is going to be 1,500 Newton. That will be the weight of the astronaut on planet Jupiter. So as usual, the third question is an assignment to my students. So attempt this. If it becomes difficulty, remember we have ECLM website where you can get a solution for that. But I think this one is very easy now. So from what we have just discussed and the calculations that we have handled, now we can give the differences between mass and weight. The first difference it comes from the definition is that mass is a quantity of matter in an object, while weight is the gravitational pull on an object. The second difference is that the SI unit of mass is kilogram, SI unit of weight is Newton. The third one is that mass is constant everywhere. You see, even if an astronaut moves from Jupiter to Mars, from Earth to where the mass will remain the same, but weight will vary. Weight varies from place to place. Then mass is a scalar quantity. We are going to see scalar quantities. It only has a magnitude, but weight is a vector quantity. Vector quantity, they have both magnitude and direction. Then we have the last one is that mass is measured using a beam balance, while weight is measured using a spring balance. Now that is the end of our lesson. When we meet next time, we will discuss vector quantities, discuss vector and scalar quantities. Until then, stay tuned.